Hey, physical science, this is Thursday, April the 16th, page 488. We're starting a new chapter. Yippee. Chapter 16. We're going to start chemistry. Sound good? Structure of the atom. There was a guy that lived in 400 BC. They say it's before the Common Era, BCE, but they're still using the birth of Christ as their starting point. I think that's kind of hilarious. I call it BC. Anyway, there was a guy by the name of, come on, help me, Democritus. Democritus believed that you could take something like this and you could slice it down, and you could slice it down, and you could slice it down, and you got all the way down to the ultimate particle, which he called the atomos. The particle that kept the physical properties, kept the properties of that particular substance. We know now as an element, aluminum. Now, atomos is the name he gave for it, and that means in Greek, indivisible. And you cut it all the way down, ultimate particles, retain properties. One nation under God, indivisible. Okay, and so Mr. Democritus came up with the idea to begin with of ultimate parts. And 2,000 years later, a guy by the name of John Dalton in the 1800s decided that he would adopt the same concept. The reason that Democritus didn't get the notoriety for it is because there was this other dude that had a different idea on things. His name was Aristotle. And of course, Aristotle carried the day, and I couldn't even remember Democritus's name. So we're on page 488, scientific shorthand. I happen to have a periodic table of elements. I would normally pass out one for you to look at, but I'm going to go over here and let you see it. Okay? Now I'll shut some of those lights out so you can actually see this. I better keep this one on down here. All right. Maybe I'm going to have to bring it over a little closer. So what we have here on the periodic table, and by the way, you know what it is, right? Go to the very back of your book. Inside the back cover is a periodic table. And over here, we have metals. And over here, we have non-metals. And along the stair-step line, we have what are called the metalloids. Okay? The symbol H stands for hydrogen, He, helium. Sometimes it's one capital letter, and the second letter is lowercase. Please don't embarrass me in college by making it capital H and capital E. Lithium is Li, beryllium is Be. So we can make heads and tails of that because the name is the same as the abbreviation called the symbol. The symbol for boron is B, carbon C, nitrogen N, oxygen O, fluorine F, neon Ne. It's a sodium thing, Na. And what's this iron thing? Fe. And let's see another one. Silver, Ag, copper, Cu. All right, well now it's time for us to look at that table on page 488. Table says aluminum is Al. It says down here gold is Au. Mercury is Hg. And lead is Pb. And those are Latin names. Argentum for silver. Plumbum for lead. And silver is Argentum Ag. I already said that. So elements are used to be put together. This was an element, aluminum, and this is water, H2O. So elements are kind of like the letters. Compounds are kind of like the words. And you take these symbols and put them together to annotate compounds. So we're going to go ahead and write some of that up here. H2O, 2 atoms of hydrogen, 1 atom of oxygen, forms this compound, water. But this is called the formula for the compound. So does the formula represent a compound? Yeah. The formula represents a compound. But it consists of elements. That are chemically bonded together. Now, does that represent 2 atoms of an element? And does the invisible one represent 1 atom? So what does O mean? Does O mean element or does O mean atom? It can be used in either way. And what does H2O mean? Does it mean formula or does it represent a compound? It can be used either way. And then I'm just going to tell you, this is called di, meaning 2, hydrogen, mono, meaning 1, oxide, dihydrogen monoxide. They drop one of the O's because that's the way we pronounce things. Page 489. An atom is the smallest particle of an element that retains the element's properties. I've already said that. And then we've got subatomic particles. Nucleus is consisting of protons and neutrons. And then there are electrons. You take a look on the top of page 489. The nucleus is very small. If you were to blow up the nucleus to the size of a paperclip and put it at the 50-yard line at Neyland Field, which is in University of Tennessee, Knoxville, the closest electron would be up in the uppermost nosebleed section of the stadium. That's where I get my cheap seats. And all the distance between those electrons and that nucleus would be empty space. So the nucleus is very small with respect to the volume of the atom. The volume of the atom is occupied by electrons that are buzzing around like bees around a hive around the outside. They occupy the empty space. They're in motion because God made it that way. He made every electron, he gave them a kick when he made the creation. And the nucleus is in the center. The protons are positive in the nucleus, and the electrons buzzing around the outside are negative. And that holds them together. But they don't want to crash in there, so God gave them a kick like the moon, and that keeps it in orbit, buzzing around the nucleus. So the opposites attract, pull it together, but the kick keeps it apart, so that it keeps that electron in a cloud of different spots that it might be around the nucleus. So let me draw an atom. Let me draw the carbon atom. If we go over to the periodic table, we're going to find that carbon is element number 6. That represents the number of protons in the nucleus. On average, it has a weight of 12, but there are some heavier carbons. You can see the 12.01. There are some heavier carbons out there. I call them chunky carbons that weigh a little bit more. So you got to specify the weight of the carbon atom that you're going to draw. Let's draw a carbon atom that weighs 14. It's radioactive because it's got too many neutrons in the nucleus. It's too big for its britches. So it's radioactive. It spits some of the particles from the nucleus out. Anyway, it's decomposing. And so carbon is element number 6 on the periodic table. That represents the number of protons, and they're positive. So I'm going to go like this. 1, 2, 3, 4, 5, 6. 6 protons. But the thing weighs 14. What's 14 minus 6? 8. So we've got 8 neutrons. And that is a nucleus. This is not to scale. I hope you understand that. Now, if you've got 6 positives, how many negatives do you need? Yep, 6. And the first 2 electrons are going to be on the first energy level. Because that circle, that sphere around the nucleus is so small, it can only hold 2 electrons. The second one can hold 8. Up to 8 electrons. But we don't have 8 more to go. Because we got 6 positives, therefore we need 6 negatives for a neutral atom of carbon. And so we used up 2 negatives, so you got 4 more. 1, 2, 3, 4. That right there we call a model. A model of the carbon-14 atom. Carbon-14 atomic model. Carbon, those 6 protons make it carbon. It gives it the identity of carbon. These 8 neutrons make it that. That's what I call it. It simply gives weight to the nucleus. These are neutral, and these up here are positive. And these out here are negative. That's why I write it as an E with a negative. They stand for electrons. And we're drawing neutral atoms right now, so you'll always have the same number of carbon atoms, of protons, as you do electrons. Let's go ahead and label those blue. These are protons. These are neutral neutrons. And these are negative electrons. Those are 3 subatomic, that means within the atom, particles. So every atom is made up of 3 subatomic particles called protons, neutrons, and electrons. Some people will say that the atom is made up of 2 particles, the nucleus and electrons. And the nucleus is positive, because that brings positive to the picture, and that neutral doesn't bring anything except weight. And so the nucleus is positive, and the electron cloud is negative, and this is where I'm getting off the wagon. See ya.